Welcome back, strange ones. This is Lance, your host of Strange Bites, where we take a real discovery from the edge of science, dress it in a little fun, and ask what it might mean for the rest of us. Tonight we go 2 kilometers underground into a place that should be dead, a flooded uranium mine in the ore mountains of eastern Germany. Cold black water, no sunlight, air so thin it might as well not exist. And in that water, something is quietly performing alchemy. Something is turning one of the most toxic radioactive metals on Earth into a solid that doesn't want to move. A compound so stable, it has already outlived the people who first noticed it. Episode 44 is a story of the bacteria that eats poison and spits out rock. For decades, the Shelma Abelrhoda mine was one of the largest uranium operations on the planet. Miners dug deep, almost 2,000 meters down, chasing the metal that powered the Cold War. When the wall came down, the market collapsed, and in 1990 the pumps were turned off. Water rushed in, the tunnels filled, the mine became a drowned labyrinth. The problem didn't go away. Uranium loves to dissolve. When it does, it turns into a mobile form. Scientists call it hexavalent uranium, or U6 for short. Think of it as the metal's travel mode. It slips into groundwater, rides the current, and spreads far beyond the old mine. Even after 30 years of expensive chemical treatments, the water still carries about 1 milligram of this traveling uranium per liter, higher than the legal limit for discharge. Most of us would look at that dark water and see only a problem. A team of scientists looked and saw a laboratory that already contained the solution. In 2026, a group led by Antonio Newman Portela decided to ask a simple question. What if the bacteria already living in that mine water could be fed? They took real mine water, the kind that still carries dissolved uranium. They sealed it so no oxygen could get in, exactly the way it is 2 kilometers underground. Then they added a little glycerol. Glycerol is ordinary stuff. It's in the fats of plants and animals. Fungi make it when they break down wood. Biodiesel factories produce it as a cheap leftover. It's sugar alcohol, food for microbes. Then they waited 130 days. When they opened the samples again, only about 5% of the dissolved uranium was still floating free in the water. 96% had vanished from solution. It had been pulled into solid form and locked inside the bacterial cells and the tiny particles around them. The bacteria had performed a quiet magic trick. 2 different spells. Now here's the part that made scientists sit up. Normally when microbes reduce uranium, they turn the traveling form UV6 into the stationary form UV4. That stationary form often becomes a mineral called uraninite, tiny black crystals of uranium dioxide. That happened here. The team found biogenic uraninite nanoparticles only a few billionth of a meter across, stuck to the surface of the bacteria. But something else happened too. Something rarer. A portion of the uranium stopped halfway. It became pentavalent uranium, U5. Scientists used to think this middle state was almost impossible to catch in nature. It was supposed to be unstable, a brief flash between the 2 more common forms. Yet here it was, hanging around for the entire 130 days of the experiment. Even after the researchers deliberately exposed some of the material to oxygen for 4 weeks, a large share of that U5 stayed put. How? It had married iron and oxygen. The result was a compound written as FeU5O4. Tiny nanoparticles of iron uranium oxide. This same compound had been spotted earlier in soils contaminated by depleted uranium ammunition in Croatia. There it had remained stable for more than 25 years, even under open air. Until this study, no one knew bacteria could help make it. The microbes were not just reducing uranium, they were guiding it into a surprisingly durable prison. So who are the alchemists? The team didn't engineer a single special bacterium. They used the natural community already living in the mine water. When glycerol arrived, certain groups exploded in numbers. Fermenting bacteria broke the glycerol down into simpler molecules, acetate, lactate, hydrogen. Those leftovers became food for another group, sulfate-reducing bacteria such as Desulfo bulbus and Desulfo vibrio. These sulfate reducers change the chemistry of the water, creating conditions that favor uranium reduction. Some of the reduction may even happen indirectly, through the iron and sulfide the bacteria produce. In short, a whole underground ecosystem shifted. The glycerol was the dinner bell. The uranium was the unwanted guest that got turned into furniture. Advanced X-ray beams at a synchrotron in France and high-resolution electron microscopes confirmed the story. The uranium was sitting inside and on the bacterial cells. The nanoparticles were real. The rare pentavalent state was real, and it was stable. So why does this matter? Cleaning uranium-contaminated water the old way is expensive and endless. You add chemicals, you create sludge, you dispose of the sludge, and the mines keep leaking. Bioremediation, using living organisms to do the work, has been studied for years. This discovery adds a new chapter. It shows that under the right conditions, a natural bacterial community, given a cheap and abundant food source like glycerol, can convert almost all the mobile uranium into solid forms that include one of the most stubborn compounds known. It's not ready for the field yet. The researchers are careful. Real mines are messier than laboratory bottles. Different pH, different minerals, different oxygen leaks could change the outcome. But the door is open, and glycerol is already a waste product looking for a purpose. So what does this all really mean? We spent the 20th century digging radioactive materials out of the ground so we could split atoms and threaten each other with apocalypse. We left behind a long, expensive mess. Now, in the quiet dark of the same mines, life is doing something we never planned. It's learning to lock the poison away. There is something almost mythic about it. The same element that once fueled weapons is being folded into the cell walls of organisms older than human history. Bacteria do not care about our geopolitics. They care about electrons and energy. Give them a carbon source and a redox gradient, and they will rearrange the periodic table to suit themselves. This discovery is a reminder that the living world is not a passive victim of our industrial age. It is an active, adaptive, and sometimes opportunistic partner. The question is whether we will treat it as a partner or as another resource to be exploited. Imagine a future in which we no longer fight contamination with endless chemical plants, but instead learn to listen to the microbial communities already present. We feed them carefully. We create the right conditions. We let them do the alchemy. The implication is both hopeful and unsettling. Hopeful because nature may already hold tools for healing the wounds we have made. Unsettling because those tools belong to organisms that do not share our values, our timescales, or our sense of risk. If bacteria can turn traveling uranium into a solid that lasts decades, what else can they turn? What other impossible intermediates are they stabilizing in the dark places we prefer not to look? And if we start deliberately feeding them, are we still the ones in control, or have we simply become another carbon source in their larger chemistry? The flooded mine is still there. The water is still cold and black. Somewhere in it, microscopic alchemists are still working, indifferent to our approval. We can choose to learn from them, or we can keep pretending the deep is empty. And maybe, just maybe, we should listen a little harder to the things that live, where the light never reaches. That's it for today's bite. I hope you enjoyed the story. If you did, please hit that subscribe button on your favorite podcast app. Give me a follow on social media. Share with a friend. And until next time, stay strange and question everything.